চলো চালু করা যাক টার্বুলেন্ট ফ্লো সব ডিটেলগুলো আমরা এখন পড়বো। এদিকেই করা ভালো, কারণ এখানে বাস্ট বলে আছে রেনাল নাম্বার ট্রানজিশন ফ্লো এখানে, দেন টার্বুলেন্ট ফ্লো বুম 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 হচ্ছে। দেন এখানে কটি ফ্লো ইজ এনার্জি ইজ র্যান্ডাম ফ্লাকচুয়েশন অফ ভেলোসিটি ডিউ টু চেঞ্জ ইন ফোর্স ইন ভিসকাস ফোর্স। ওকে, এগুলো সব লেখা আছে। ক্যারেক্টারিস্টিক কি হেভি মিক্সিং হবে, motion of the fluid particle is highly unpredictable হবে, even the overflow of the fluid unpredictable. All the components of the velocity are present in the turbulent flow. Velocity at any point of the turbulent flow continuously changes with respect to time. It's a very common thing, and it's a random flow. Kinetic energy and potential energy relatively high, velocity is close to uniform velocity, and random intermitting fluid parts between them, extra shear force due to momentum and thickness. These are all the things. Now there is a velocity. There is a two type of velocity, that is time average velocity and the random fluctuation velocity. Time average is denoted by u bar and random velocity is denoted by u dash. Total we can say u equal to u dash plus u bars. In second video then we can get instantaneous velocity and time average velocity and fluctuating velocity, all those things. So what is instantaneous velocity? It is the velocity of the turbulent flow at any given instant, and it is indicated by u, v and w, those things. Now coming to second, time average velocity. It is the average instantaneous velocity. It's the average instantaneous velocity at any point over a sufficiently large time interval. It is velocity by u bar to u bar. So it is dA equal to u dt, that is u bar dt. That's how u bar equal to 1 by t, u bar equal to 1 by t 0 to 2 e dt, 1 by t 0 to 2 u dt, v bar equal to 1 by t 0 to 2 v dt. That's how we have been formulating for the velocities. And now fluctuating velocity, it is a difference between the instantaneous velocity, it is a difference between instantaneous velocity and time average velocity. Both of this, that is u minus u bar, that is the velocity, that is fluctuating velocity. So but average random fluctuation, that is u dash, that is 1 by t 0 to t u dash dt, not useful here. Now f bar we can see f1 plus f2 plus f3 dot 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 by n. Also we can see n dx. Also we can count f bar equal to, so f bar means time average velocity, a to b f bar dx by b minus n. That is the difference between the n bar dx. Now the most important is, so we are taking 1 square then adding the, so u bar square, u bar dash square equal to 1 by t 0 to 2 u dash t t. Now most important, that is the RMS value, root mean square, that is u root mean, that is u bar mean, then square, that is 1 by t 0 to t then u dash dot dt. The RMS random fluctuating velocity. Instantaneous turbulence is 1 by 3 u dash bar dash square, that is the RMS velocity square, v dash l dash square. Then we think, but we can't eliminate the 3. Now the shear stress in case of turbulent flow, what is happens, tau equal to minus dp by dx into r by 2. It has seen by the boundary layer thickness, but here one is one more, tau into mu into dy by dy, that is previous like the laminar, but there is a tau turbulent, that is the momentum transition transfer, that is also here. So in turbulent viscosity, velocity is not sufficient. Additionally, due to momentum, there is a random collision of development. So flow above the, we are getting tau equal to tau viscosity plus tau turbulent, tau velocity plus tau turbulent. These both are adding up, then getting, it is the tau laminar. So tau laminar is tau laminar plus tau turbulent. So Reynolds model for tau turbulent, it is tau turbulent equal to rho into u dash v dash. That is not important. U dash is random fluctuation in x axis, v dash in y axis. So you can see same way tau turbulent is rho w v, it is rho w dash v dash u dash. So now Gaussian equation. So I don't think it is very useful. So Gaussian is u, this thing you must remember. N is eddy's viscosity, then mu into n, that is eddy's viscosity du by dy. So mu into du by dy, something happens, but in this case mu plus niter. It is property, or it's not a property of the fluid. It varies continuously with different condition. When n0 is 0, then it is the, yeah. This is front end model. Also there is there. It's not also as a compression of Gaussian front end. That is also, I don't think it is useful, but you just have a look. There is a mixing, that is L equal to K into Y, that is the linear proportionality. Lateral motion, that is L into K into Y. K is the Kerman constant, that is 0.4, and all of the 5, that is the Y equal to 0 distance, like in adjacent to the layer there is a L0. The n value would be 0, tau turbulent also will be there because there is a laminar flow that will happen there. So the tau shear stress will be laminar plus addition of laminar plus turbulent flow. So tau shear will be tau laminar only, because there will be no turbulent flow in that case where the y, the distance from the boundary, from distance from the wall is 0. So tau 0 equal to mu into du by dy. So now shear velocity to frictional velocity, or shear velocity of frictional velocity, that is v star. The standard formula equal to V star equal to tau 0 by rho. V star is equal to root over tau 0 by rho. F equal to 4 tau square half rho V. I don't think it is internal flow we are getting. So tau 0 by rho equal to F by 8 dot V square. Tau 0 by rho equal to F by 8 dot V square. Okay. Now putting all this value aside, we are getting the main equation. It is V star, that is the average velocity. V star is the average frictional velocity is V into F by 8. F is frictional action, F is the shear velocity, average velocity, and V star is shear velocity. Okay, velocity profile for the turbulent flow would be, this is the velocity profile for the turbulent laminar. It is further more. So turbulent velocity profile almost prefers rectangular. It's almost like the rectangular profile. No? Laminar is almost like parabolic. So as the alpha value is increasing, and now what is alpha? You may ask that alpha is the kinetic energy correction factor that you need to remember, and more steeriness, more inward. So less intensity, less, so more intensity, more inward, and less intensity, more like laminar profile. Okay, now Navier equation also useful for these cases. You just remember. So du by dx plus du by dy equal to 0, that is the Navier-Stokes equation. And also we can see Navier-Stokes is that, yeah, it is, I have seen that x equal to mu into delta square v by dp by dx plus rho gx, delta square v by dp by dx into rho gx. That also we have seen many cases we have been applying this. So now turbulent flow over a flat plate, we are getting turbulent flow over a flat plate. How is happening? So due to the frictional velocity, instantaneous velocity, we can say experiment shown the velocity profile viscous sublayer is overlap logarithmic, where in outer shape the velocity profile cannot be predicted. Outer region there is a velocity profile that we cannot predict. The thickness where viscous layer is delta V. So delta V is the thickness of the boundary layer, that is 11.6, that is denoted by, remember, that is 11.6 mu by V star. V star is the kinematic viscosity. Shear velocity, V star equal to shear velocity, that is tau W by rho, and V is kinematic viscosity. The flow in the xy component of the Reynolds number is determined by tau star equal to rho u dash v dash. So by parallel mixing length above the component, Reynolds number is given by, so there is a mixing of the length. So basically this is the tau star equal to mu into ut into turbulent by du by dy. That is, you have seen dynamic viscosity properties depends on the velocity fluctuations. Now shear stress profile, there is a three region, that is the one region, two region, that is a three region. One is a laminar sublayer region, two region is the overlapped region, three is the outer turbulent. There is a tau turbulent is 0, a tau laminar is 0, that is the outer layer. A turbulent is 0. Region 1, it is mu to du by dy. The question, velocity profile and laminar profile. Velocity profile in laminar is almost linear. Region 2 is almost linear. Laminar sublayer thickness, that is delta star equal to A into V by V star, A into nu by V star. Also we can see that 11.6 nu by V star, that is laminar sublayer thickness. It is important for roughness characteristic of the pipe. So we know that tau 0 equal to minus dp by dx into r by 2, tau equal to minus dp by dx into r by 2. We know. Now tau laminar plus tau turbulent. So this is the part where we are getting laminar flow, and this is the part where we are getting turbulent flow. So velocity profile in turbulent flow almost flat center, because high mixing of the turbulent flow get almost uniform distribution. Now near to the surface within the viscosity sublayer, the sharp variation of the velocity because the mixing in the viscous sublayer. In turbulent pipe flow, outer layer is usually not observed because the pipe central line is reached before the overlap of the finish. Here the turbulent velocity profile is the most internal region. Okay, the logarithmic profile is the different equation for the smooth and rough pipe. So the logarithmic profile is the approximate by the profile equal to u max into 1 minus r by r to the power n. Now topic is the roughness of the pipe. As there is a layer, that is a barrier, there is a laminar flow, above this is the turbulent flow. Okay, so there is no eddy formation would be there, it is not existing in the surface roughness. So surface hydrodynamically smooth surface. So E is the average height of the irregularity. So E is the surface roughness. Remember, many times it's come. E is the surface roughness, the average height of the irregularity in the inner wall, the average height above which, so this is called E. Okay, E or K, something we got. Turbulent flow is the property of two things. Turbulent flow is a property of two things. That is, one is Reynolds number, another is surface roughness, that is denoted by eta or epsilon, whatever you can say. Laminar flow is the more than surface roughness. Laminar flow is more than surface roughness. So what we are saying is the laminar flow is more than the surface roughness. Okay, hydrodynamic is smooth surface, that is function of only Reynolds number, because E will not be any role. And range is the, remember, Bacillus equation of the friction, that is 0.31x. The friction factor, that is F, we can denote is 0.316 Reynolds number to the power 0.25. And the range for this is the E by delta star. Delta is the boundary layer thickness, and E is denoted by E is denoted by surface roughness, that is less than, that has to be less than 0.25. Okay, so this equation Bacillus is only, as far I can know, that is for the laminar flow only, because it is less than 10 to the power 5, so it just denotes the laminar flow for this equation. Okay, hydrodynamically smooth surface, the next thing that we are getting. So hydrodynamically smooth surface, how can see K, that the surface value is just less than 0.25 V, that is hydrodynamically smooth surface, and rough surface is where the K is greater than 6 greater than V. So experimental data is E by delta square is greater than 0.6, the friction factor would be only E, so 1 by F. So Nicaruda's equation is 1 by root over F 2 log 10 R by E plus 1.74. So I don't think it is very much needed. So pipe in transition, when pipe is transition, there is a central line, there is a laminar, and there is a surface option dose. So 0.25 to 0.6 delta by E by delta star, that is the value. So while laminar flow surface roughness was not important, here's the question. So E by star equal to delta is 11.6 nu, that is nu by V star. So 11.6 V star, that is average dynamic velocity by V star. Okay, now turbulent flow, there is a couple of equations that are important that I will share. So let me just remove this thing first. So delete. Now start. Shear velocity is the V equal to V into V star equal to V into V star equal to, for shear velocity, that is V star equal to V into F by 8. Also you can see root over tau 0 by rho. And now F equal to Umax into V into V star. So Umax minus V by V star equal to 3.75. And F of Umax, V, and F is a friction factor. Umax by V equal to 1 plus 1.43 root F, place putting the value of V star. How is happening? So smooth 5, then U by V star equal to 5.75 log R minus R V star by nu plus 5.5. And Umax, putting the above value, Umax by V equal to 5.75 log 10 R nu star R V star, that is average velocity, kinematic friction velocity by nu, average velocity by nu. So V by V star equal to Umax minus 3.75 in this case, and V by V star equal to 5.75 log R V star by nu plus 1.75 now. So mainly both four first equations are really important, but neither we don't need to remember. Then we are coming to the rough pipe case. So first equation that is very important, that is U by V star, that is the average velocity divided by the velocity. So that is the equation is m 5.75 log 10 R minus R by epsilon plus 8.5. That is the equation we are getting. And U max by V equal to 5.75 log R by E plus 8.5. And putting with all the value, so we are, there is a commercial pipe that is coming, is the surface roughness, we have said, is known as the surface roughness. E by delta star equal to velocity into new dynamic factor. So now first problem, equivalent. So equivalent pipe surface, that is D equal to T for equivalent, and for smooth pipe we are getting E equal to E into S we are getting. Now Colebrook equation, implicit formula to derive, but heat and trial. So for use, 1 by root over F equal to minus 1.8 log 10 e to the power S by 8, 3.7, 1.1, 6.8 by what is e to the power S, that is the value. That is, we see equivalent pipe, that is the surface roughness, the rest we are getting. Now the equation is e to the power S by D. So it's not clear. So if friction factor is the sense only for Reynolds number, so its Reynolds number, it is increasing in this line, so E by S is decreasing. So as we are, ES by T is increasing, ES by T is increasing, roughness releasing, and high dependence of RE. So how is growing? Let's have to see. Okay, I don't think I know more thing.